Okay, welcome to OLO4, which is an online presentation basically on the effects of exercise on ventilation or breathing, and maybe slightly we'll have a quick look at the effects of exercise on respiration or gas exchange as well, but particularly looking at exercise and ventilation. Now you might say, firstly, why is this such a significant thing to look at? Well, surely I don't need to really think too hard to work out that in fact during exercise your body tissues are working at a greater extent than normal. As a consequence of that, the body tissues are producing more carbon dioxide than normal, so systemic venous and arterial PCO2 would go up. This would increase the concentration of hydrogen ions in the blood, which will stimulate the central chemoreceptors, which will stimulate increased ventilation via increased activity along the phrenic and intercostal nerves. We spoke about that in the live lectures, the process. And this is a classic example, you might think, of negative feedback. We induce a challenge, exercise, we increase PCO2, the body's negative feedback responses occur, so we get an effect which aims to reduce PCO2 or hydrogen ion concentration levels back to normal. Well, it all makes sense, but it's wrong. The increases in ventilation or breathing we see in exercise fall outside of the auspice or the general rule of negative feedback. So we'll explore what we know about this as we go through this online presentation. Now notice the first overhead I use is labelled spirometry, because in fact what I'm going to show you is some data taken from a student undergoing a series of breathing episodes with changes in exercise intensity. Now if you look at this video, clearly for those of you who do PTB, the physiology prac subject, you'll be familiar with this because you've undertaken this activity in your prac classes. For those of you who don't do the prac subject, this may be, the word spirometry may not mean too much to you. So I'll take you through the process very quickly. We'll replay that again. Here we have a student volunteer. Thank you, volunteer, for connected to a spirometry. Basically, she's got a breathing mask from which and into which she is breathing or ventilating. There's a filter which basically just removes saliva or any particulate matter. She's breathing then into a spirometry measure, which basically looks at the changes in pressure when she's breathing and converts that to a trace on the screen. So you can see that the trace on the screen indicates changes in pressure and volumes as somebody is breathing. So this is the process by which we can measure what's going on. This is the trace that we get, which is cranked up in complexity somewhat, and I'll take you through what this trace actually means. And I apologize for some of the writing being particularly small. It's not right writing, the printing on the screen, but I'll take you through it. It's not that important. On the y-axis we have a number of different modalities that are measured, and I'll take you through each of those. Some of significance, some aren't. And on the x-axis we have time. So hopefully you can see that each of these components are in blocks of 2 minutes and indicated on the x-axis. Now what are we looking at and what did we measure? As I said, some of these are relevant to this conversation and some aren't. It doesn't matter, we'll select the ones that we're interested in. The bottom screen in purple, we have a trace of tidal volume, obviously the amount of air that's breathed in and out per breath. In the second trace in brown, we see the respiratory rate, obviously the rate at which you are ventilating or breathing. And we'll come back to these and focus on them in a moment. In the, what colour would that be? Pale green, aqua, whatever. That trace, we see heart rate. Now, you would obviously predict that with changes in exercise, heart rate might change, but that's something which was done in semester 1. or in year 1 if you didn't do PTA in semester 1. You're familiar with those changes. The dark blue trace gives us respiration, which in fact is inaccurately labelled according to this machine. I think I need to speak to the ADI people who produce this and get them to recognise that respiration is wrong. It should be ventilation. It should be pulmonary ventilation. So it's looking at the change in pulmonary ventilation. We'll talk about that in a bit more detail later on. The pink line gives us temperature, body temperature. The green line gives us ECG. Now you might say, oh, I know about ECG, and we're looking at PQRS waves. This looks nothing like the PQRS trace. It just looks like a lot of scribble. Well, in fact, there are lots of PQRS traces in there, but don't forget that the time frame we're looking at is minutes. So this distance here would be approximately 4 to 5 minutes. And obviously there would be, at normal heart rate of about 70 beats per minute, there'd be 350 ECGs in that distance. So obviously they're compressed somewhat. We don't see the individual components. They are there, compressed time frame. The blue, pale blue, we see percentage of CO2, and the red line we see percentage of oxygen, and I'll talk about that in a moment as well. And what do all these blocks mean, these dashed lines? Creating different segments. Well, here we have the subject breathing normally at rest. Then we have the subject breathing during light exercise, about 5 minutes. Then she undertakes 5 minutes of medium exercise, undertakes a further 5 minutes of intense exercise, back to 5 minutes of medium exercise, and then she stops, and we have a number 5 or so minutes of recovery. So they're the blocks of activities. Now what can we learn from this? Well, we learn that obviously when you're exercising, tidal volume increases. So this is it at rest. Obviously with different intensities of exercise, we get ever increasing depth of breathing. So you breathe more deeply whilst you're exercising. What about respiratory rate? Well, during rest, it is this rate. Does it go out significantly during exercise? It goes up a bit, but not significantly, certainly nowhere near as much as tidal volume. And when you consider that's in fact totally appropriate, and we may have even touched on that in the live lectures, if you want to increase your pulmonary and hence alveolar ventilation, you've got two choices. You can breathe more deeply, tidal volume increase, or you can breathe more rapidly, respiratory rate increases, or you can do both. Which is most energy efficient? That in terms what can you do with the expending the least energy increase? Well, when you consider it, if you increase respiratory rate, you're getting a lot of work, but don't forget that the first 150 mils of every extra breath you take is still dead space, which is not going to contribute to respiration or gas exchange, or in fact increase alveolar ventilation. But if you use the same energy to increase tidal volume, or the depth you breathe, every extra mil you breathe on top of your normal tidal volume is atmospheric gas, high in oxygen, low in carbon dioxide. So if you had the choice of expending energy by increasing respiratory rate or increasing tidal volume in order to increase pulmonary and alveolar ventilation, we choose to increase tidal volume, and you can see evidence of that and hopefully understand reasons why we do it with that explanation I just gave you. So we see this person's acting appropriately. She increases her tidal volume, increases respiratory rate a little bit in order to increase a massive increase, in order to achieve, I should say, a massive increase in pulmonary ventilation. What about CO2 and oxygen? Well, it looks as if CO2 increases immediately upon exercise. And it does, but don't forget this is percentage of CO2 in expired gas, what you're breathing out. It's not the CO2 in your blood, it's the CO2 that you're breathing out. So obviously, if you start exercising and increasing your breathing, the percentage of alveolar gas, which is proportionally higher in carbon dioxide, is greater than a normal breath. And that explains the immediate increase in CO2 percentage of expired gas. Similarly, immediate percentile decrease of oxygen is explained by the same process, that proportionally, if you're breathing out a bigger breath, proportionally more of that breath comes from the alveoli, which inherently has lower oxygen than the atmosphere. What's important or interesting in this trace? Well, the premise was if you exercised, you increase your CO2. That, as I said earlier, that would stimulate your central chemoreceptors, increase ventilation. But you can see that in fact immediately you start exercising, even if it's light exercise, you get an immediate increase in ventilation, particularly an increase in tidal volume. Now, that immediacy of the increase tends to suggest that it's not controlled via negative feedback. The other thing we see is that if we ignore the initial increases, which I explained to you earlier in CO2 or decrease in oxygen, that we get a relatively constant percentage of CO2 exhaled irrespective of changes in exercise. So the oxygen exhaled and the amount of CO2 exhaled is relatively constant throughout this whole experiment, even though the person is exercising with different intensities and hence is breathing or ventilating with massively different intensities. So we learned from that in fact the negative feedback scenario we postulated might be the cause of changes in breathing or ventilation during exercise is not true. Now let's go on and look at what's in the textbook, because that's a little bit more clear, because obviously it just focuses on the issue at hand. And I've taken this from Widmeyer figure 1342, which reminds you that a lot of this information you can see in your textbook and read about it for clarification, should you need to. Now, this diagram looks at pulmonary or minute ventilation on the y-axis, over time on the x-axis, during rest, a period of exercise, and period of recovery. And you see basically what we saw in the last trace, that the person's ventilation is constant whilst they're resting. They start exercising, there's an immediate increase and a fairly significant increase. So this instantaneous hyperventilation upon the onset of any exercise suggests that it's not caused by in response to negative feedback. It's almost an anticipatory response, increasing your ventilation, anticipating the increased oxygen and increased need to get rid of carbon dioxide whilst you're exercising. It can change during exercise, and it does. And when you finish exercising, there again is an immediate decrease. Note it doesn't go back to rest immediately, but there's a significant immediate decrease, again telling you that it's obviously not driven by negative feedback. The fact that it's not returning to pre-exercise levels is simply just explained by this oxygen debt. So after exercise you have a small period of time where you're trying to restore your myoglobin and creatine phosphate, the processes involved in energy production and acid cleanup, removing excess hydrogen ions, and that's why it doesn't return to base levels. But it returns to base levels nevertheless fairly quickly. Again, giving us proof, back to that same thing. It's not negative feedback that seems to be driving this. Let's look at it in a little more detail again, and this is again showing what we saw in our real life demonstration in slide 2, but it's just looking at it in a bit more simplified form. Taken this from Widmeyer figure 1341. Different modalities: arterial hydrogen ion concentration, arterial PCO2, arterial PO2, and pulmonary or minute ventilation in green. Period of rest on the left on the x-axis, and the process, the change that happens with exercise, and we're increasing the intensity of the exercise as we move to the right. So what do we see? As we saw earlier, as verified earlier, we see that with exercise there's an increase in pulmonary ventilation or minute ventilation, and this is somewhat proportional to the amount of exercise you are doing. But we don't get any change in the partial pressure of oxygen, nor do we see any change in the partial pressure of CO2. In fact, these changes in ventilation seem to be preventing changes in oxygen and carbon dioxide rather than responding to them. Negative feedback says we respond to a change. This is preventing a change, totally opposite to negative feedback. We also see, unsurprisingly, because of the close link to partial pressure of carbon dioxide and hydrogen ion concentration, that where there is no change in carbon dioxide, there is also no change in your pH or your hydrogen ion concentration. Until we reach a certain critical threshold level. So you can see that when your exercise becomes very intense, we start to get not an increase in carbon dioxide, but actually a decrease in carbon dioxide and an increase in hydrogen ions, or a decrease in your pH. So what's going on there? Well, let's have a quick look at that as well. It comes down to something called anaerobic, or some people call lactate threshold. And I can't show you something from Widmeyer because it's not there, so I've taken something from Byrne and Levy, which is a fairly advanced physiology textbook. You don't need to look at the textbook beyond this diagram. It's fairly self-explanatory. It's so simple that it has no units on the y-axis. It doesn't need to. These are just basically different modalities, which I'll take you through in a minute. And on the x-axis, which is significant, is the VO2, which is your oxygen consumption, how much oxygen you use in litres per minute. Now, we learnt in our live lectures that at rest your oxygen consumption is about 250 mils per minute, a quarter of a litre, so somewhere around here. So this is a good starting point. At rest, your ventilation would be a certain amount. There's no scales here, we don't really worry about the numbers, but you and I know that that ventilation, if it's alveolar pulmonary ventilation, would be about 6 to 7 litres per minute. At rest, your partial pressure of CO2 in the artery, PaCO2, which is this one here in fact, would be about 40 millimetres of mercury. We learnt that in the lectures. Your P arterial partial pressure arterial oxygen would be about 100 millimetres of mercury. We've learnt that in the lecture. Your lactate levels, I don't even know the units, I don't care about the units, but they're constant as well. Now, when you start exercising, and hence your requirement for oxygen increases, your cells need more oxygen. As we just saw in the last overhead, ventilation increases, but we don't get any changes of the other modalities until we get to a critical level. And that critical level is called, as I said, the anaerobic threshold or lactate threshold. And it's really the point in exercise intensity at which the lactate, or more specifically lactic acid, and the key word is acid, starts to accumulate in the bloodstream. So it's basically at this threshold point, we're seeing this is the point in your exercise intensity that in fact your lactic acid is produced faster than it can be removed by the muscles, and hence it increases in your bloodstream. Now, lactic acid, it's an acid, obviously. It's going to decrease blood pH, obviously. That decrease in blood pH is going to stimulate your peripheral chemoreceptors, not the central ones, because this pH change is not caused by changes in carbon dioxide. It's caused by changes in tissue metabolism. So the peripheral chemoreceptors respond to that decreased pH, or the increased acidity, and increase your ventilation. So we get a massive increase in ventilation stimulated by your peripheral chemoreceptors. Now, this is so great, and it's not controlled by CO2, that in fact this massive increase in ventilation has the effect of actually blowing off quite a bit of carbon dioxide, which is why we get this quite significant drop in partial pressure of CO2. And that explains what we saw in the last overhead. Back to point. Ventilation and exercise. What have we kind of seen thus far? Well, I've tried to hint to you, or in fact said quite specifically to you, that the cause of this increased ventilation during exercise remains largely unknown. We don't know why your breathing increases during exercise. It's not negative feedback. No single mediator or mechanism has been identified thus far. You kind of think we should know everything there is to know about the body, but we don't, and this is an example. No single mechanism has been absolutely identified as explaining why ventilation changes relative to CO2 production, and we know that hypoxia, which is basically low oxygen, or hypercarbia or hypercapnia, same word, well, not the same meaning, it's not the same word, same meaning, which is increased CO2. So decreased oxygen, increased CO2 is not playing a central role because it doesn't happen during exercise. So what, if it's not hypoxia or hypercapnia, what is it? Well, we think it might be neural inputs from the motor cortex or to the respiratory centers. It may be afferent neural activity from muscles and joints, so proprioceptive activity, or it might be other mediators that we don't really fully understand. So we'll finish with an overhead from Widmeyer, figure 1343, which tries to demonstrate the things that we know or hypothesize about increased ventilation during exercise. Why, when we start exercising, do we get an instant increase in breathing? Maybe because it's the motor cortex. It's basically a conscious thing. You decide to do it. Maybe part of that is it's coming from proprioceptive inputs from skeletal muscles. So when your muscles start moving more than they would when you're resting, that stimulates the respiratory center to increase its activity and hence increase your breathing. Maybe it's proprioceptors coming from the joints as well, which is when your joints are moving more than normal, you are getting input to the respiratory centers, stimulating increased ventilation. Maybe it's humoral, that is, it's chemicals. It might be an increase in plasma adrenaline, epinephrine, same thing, or potassium, which increases and that stimulates the respiratory center as well. And remember, adrenaline happens even when you're thinking. It's a fight or flight thing, so it's even when you're thinking about exercise, it might adrenaline might increase and hence stimulate breathing. It could be a conditioned response, that is, you learn to do it over time. It could be an increase in temperature. Now, I'm going to flick back to overheads, and I don't like doing this, but I hope it doesn't confuse you. Just go back. If we looked at the real data and the temperature was in pink, you see when the person starts exercising even lightly, there's an immediate increase in body temperature by about 1 degree of Celsius. It's significant. It's not huge, but it's significant. Now, why? You haven't even started exercising. You're just starting and you get a change in temperature. That increase in temperature may also stimulate the respiratory center to increase ventilation or breathing. Or it could be oscillatory changes in PO2 and PCO2 and hydrogen ions. Now you might say, hang on, you've just told me that that doesn't change during exercise. I've seen that it doesn't change during exercise. Well, they're average levels. So oscillatory changes might be very rapid or even microscopic changes that happen so quickly we don't see them when we're looking at an average chart. So there may be jumping up and down. It's a bit lowbrow, but jumping up and down of partial pressure of oxygen and carbon dioxide and hydrogen ion concentrations that happen so rapidly that we don't really see them in average, and that those oscillatory changes might stimulate the respiratory center. The question mark says that this is purely hypothetical and there's no evidence to suggest that happens, but it may, doesn't mean it doesn't. So that gives you an idea of the complexity behind what we thought might have been a very simple process of explaining why ventilation or how ventilation changes during exercise.